Today we're starting Chapter 4, which is all about forces between particles. So just as a refresher, we're going to go over the number of valence electrons that an element has because that is going to have an effect on how atoms interact with each other, and then the forces that occur between atoms or molecules really does depend on the number of valence electrons. So remember that valence electrons are the highest energy electrons. In an atom. And one really great trick is we can determine the number of valence electrons based on the Roman numeral group number. So down below we have a periodic table and it's showing the number of valence electrons in each group. Now it's only showing the valence electrons for representative elements. We're ignoring the transition elements in the middle because they kind of do their own thing. They have less predictable trends, so we tend to ignore them. Now, if we go across and label each of the representative columns, we have 1A, 2A, and then we're going to jump over to 3A, 4A, 5A, 6A, 7A, and 8A. And I left out the A's just because I ran out of room. So you'll notice that everything in group 1A has one valence electron. Everything in group 2A has two valence electrons. Everything in group 3A has three valence electrons, so on and so forth. And then in group 8A, everything has 8 valence electrons except helium. So helium is our exception here. Now remember that helium has an atomic number of 2. So that means it has 2 protons and then 2 electrons. So the reason helium, though, is listed in group 8A is due to the fact that it has very similar chemical properties to the other elements in that column. Now, one way that we can represent valence electrons is with Lewis structures. So this is a representation of an atom or an ion, which we'll talk more about in a second, in which the valence electrons are represented by dots arranged around the elemental symbol. So down below we have what are called Lewis dot symbols for the representative elements. And in group 1A, again, every atom has only one valence electron. So we would just show that with a single dot next to the element symbol. So the dots again represent electrons. And then in group 2A, everything has 2 valence electrons, and we're going to represent those 2 valence electrons as 2 dots. Now, you'll notice the dots are not paired up, they're separate from each other, and you don't necessarily have to place them on opposite sides from each other. So if we look at magnesium, initially we have these 2 dots opposite each other, but you could also write this with 1 dot on the side, 1 up above, or maybe one's up above, one's down below. You can really put those anywhere as long as they're not on the same side. And that will become important later. And then when we get to group 3A, everything has 3 valence electrons, and those are represented by dots. And those dots are not on the same side, they're all on different sides. And then in group 4A, everything has 4 valence electrons. And again, you'll notice that the dots are on separate sides. Then when we get to group 5A, everything has 5 valence electrons, but we've run out of sides. So we're going to pair 2 of the electrons. So when we're writing that out, we write the symbol, and then we count 1, 2, 3, 4, and then the 5th electron can pair up with any of those other electrons. So maybe instead of pairing them on the top, we pair them on the side, or we could have paired it on the right side or on the bottom, just as long as we have one pair of electrons. And then in group 6, we're going to have to pair up yet another set of electrons. So for instance, if we have 6 valence electrons, we start with 1 electron on each side, and then we start to pair them up, and maybe we pair up the one on the top and the one on the left-hand side. And then we keep going. In group 7A, we have 7 valence electrons, so 6 of those electrons will be in pairs and 1 will be by itself. And then in group 8A, we have our noble gases. And you'll notice that with the noble gases, we're going to have electrons all paired up. So if we're writing this out, we have 1, 2, 3, 4, 5, 6, 7, and 8. Now this kind of goes back to our discussion of noble gases and some of their characteristics. So noble gases are really stable, and they don't really want to interact with other elements or molecules. They would prefer to just do their own thing, and that's partly because all of the electrons are paired up, all of the electrons are happy. Now you will notice helium is our exception. Helium only has 2 electrons, but they are drawn as a pair because helium is stable and its electrons don't really want to interact with any other atoms. All right, so let's go over a couple of examples here. So again, potassium, which has the symbol K, is in group 1A. So it has 1 valence electron. And the Lewis structure would be K with 1 dot next to it. And then aluminum is in group 3A, so it has 3 valence electrons, and its Lewis structure would be the symbol for aluminum with 3 dots surrounding it. And then down below I have a little chart just focusing on the group 1A elements, and we have the noble gas notation for each element in that group. And you'll notice that we're adding energy levels each time, but that highest energy level always has just 1 valence electron. So each of the elements in group 1 has just 1 dot next to its symbol. And these Lewis dot symbols or Lewis structures are really important because we can use them later on to try to figure out the structure of a molecule, or we can also use it to help us figure out how many electrons might be transferred to another atom or shared with another atom. So these will come in handy. All right, so let's draw the Lewis symbols or structures for all of the elements in row 3. So what I'll do is write out all of the elements in row 3 of the periodic table. So that's sodium, magnesium, and then we're going to skip those transition elements, and we're at aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay, so sodium is in group 1, So it has one valence electron, and I'll just draw it on a random side. And then magnesium is in group 2A, so it has two valence electrons. I'm just going to draw those wherever I want. And then aluminum has three valence electrons like we saw earlier. Silicon is in group 4A, so it has four valence electrons. So we're going to draw one on each side. And then phosphorus has five valence electrons. So I'm going to just kind of work my way clockwise. 1, 2, 3, 4, and then the fifth one pairs up with one of the other electrons. And then sulfur's in group 6A, so it has six valence electrons. So I'm just going to go clockwise, and now I need two more electrons, so I'm just going to pair them up with two of the other electrons. And then chlorine has seven valence electrons because it's in group 7A. So I'm just going to go clockwise again and then pair up my last three electrons. And then argon has 8 electrons. It's in group 8A. So I'm just going to start at the top, move my way around, and all of the electrons will be paired. All right, so I encourage you to do this for really the first 3 rows of the elements because, again, these will come into play later on when we draw molecule structures. So it's really important to know how many valence electrons each element has. Now, this is going to lead us into types of bonding in chemicals. So we have two main types of bonding. There's ionic bonding and covalent bonding. So in ionic bonding, electrons are transferred between atoms. So we're going to go over ionic bonding today, and then later on we'll go over covalent bonding. And in covalent bonding, electrons are shared between two atoms. So we have two different ways that electrons can be used for bonding. They can either be transferred or they can be shared. Now, within ionic bonding, there are a couple of different types of ionic compounds. There's what we call binary ionic compounds, and then there's also ionic compounds that contain what are called polyatomic ions. So we'll talk a little bit more about each of those as we go through chapter 4. Now, what's really driving the transfer of electrons or the sharing of electrons is what's called the octet rule. So according to the octet rule, atoms will gain, lose, or share sufficient electrons to achieve an outer electron arrangement identical to that of a noble gas. So remember, noble gases have typically 8 valence electrons, other than helium. So this arrangement usually consists of 8 electrons in the valence shell. So kind of the shorthand way of saying this is all atoms want to be stable like a noble gas. Or you could think of it as noble gases are the cool kids, and all atoms want to be cool. So, having 8 valence electrons is the cool new fad that all of the atoms want to follow. But in chemistry terms, we said noble gases are really stable because all of their electrons are, paired up, they're happy. So all of the other atoms want 8 valence electrons so that they can also be stable and happy. So first, let's talk about transfer of electrons, so ionic compounds. We had kind of gone over ions at the end of chapter 3. So you might remember the example of lithium losing an electron. And again, the reason that atoms will lose or gain electrons is to be like a noble gas. So a simple ion is an atom that has acquired a net positive or a net negative charge by losing or gaining one or more electrons. So for example, sodium, let's see, so sodium we said had 3 energy levels. So we'll draw the Bohr model of the atom here. And it has 11 electrons, so 2 in the first energy level, and then 8 in the second energy level. And then it just has 1 electron hanging out in that third energy level. So that's its valence electron. Now, if it loses that electron, it's only going to have 2 energy levels and 2 electrons in the first energy level and then 8 in the second energy level. So now it has 8 valence electrons, like a noble gas. And in fact, it has a total of 10 electrons, just like neon. So the way that we can write what's happening here is initially we have pure sodium, and then this arrow is indicating that we have a process occurring. And after that arrow, or after this process, we have our sodium ion and 1 electron as our products. Okay, so the reason that sodium is positively charged, so initially sodium has 11 protons and 11 electrons, and that comes from its atomic number. But after it loses that valence electron, it still has 11 protons, because remember, protons define which element we have, but it only has 10 electrons. So if we take that difference, we end up with a 1 plus charge. Now, chlorine kind of goes through the opposite process. So I'm going to erase these pictures and draw them for chlorine. So chlorine is also in row 3 of the periodic table, which means it has 3 energy levels. And then it has 17 total electrons. So 2 are in the first energy level, 8 are in the second energy level, and then it has 7 in the third energy level. So remember, it has 7 valence electrons. Now, chlorine is a nonmetal, and it's on the right-hand side of the periodic table. And remember that from our ionization energy trends, anything that's on the right-hand side of the periodic table has a really hard time losing electrons. So they have really high first ionization energies. So instead of losing an electron, anything that's really on the right-hand side of the periodic table or any of the nonmetals would prefer to gain electrons. So remember, I had briefly mentioned that metals lose electrons and then nonmetals gain electrons. So now let's draw what that would look like if chlorine gained an electron. So it still has 3 energy levels, but now it has an extra electron in the outer energy level. Okay, let's see, did I... 1, 2, 3, 4, 5, 6, 7, 8. Yes, I have 8 electrons in that outer energy level. So initially, chlorine has 17 protons and 17 electrons. And then when it gains an electron, it still has 17 protons, but now it has 18 electrons. So if we do the math, we'll end up with a 1 minus charge at the end. So chlorine, again, would prefer to gain 1 electron rather than lose 7 electrons to become like a noble gas. Okay, so now the way we represent this is with the equation shown below. So chlorine with 7 electrons initially, or 7 valence electrons, is going to gain 1 more electron, and then it becomes like a noble gas with 8 electrons. However, the balance between protons and electrons is thrown off. So now we have 1 extra electron, which means we have an extra negative charge. So we're going to show that up above. All right. So again, let's go over a few more examples. So magnesium, for instance, so magnesium is in group 3 as well, so it has 3 energy levels, and it has 12 electrons. So again, it has 2 in that first energy level, 8 in the second energy level. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. And then it has 2 in the outer level. Now, magnesium is going to lose both of those outer electrons because it kind of has to in order to have 8 electrons like a noble gas. So once it loses those 2 electrons in the outer level, now it only has 2 levels and 10 electrons. So what the charge ends up as is, let's see, so magnesium originally has 12 protons and 12 electrons. But then after it loses those 2 outer electrons, it still has 12 protons, but now it only has 10 electrons. So if we take that difference, we'll end up with a 2 plus charge. So we're going to write this as magnesium 2 plus. Now, what's really great is that the charge on magnesium also lines up with the Roman numeral from its group. So magnesium is in group 2A. It has 2 valence electrons. And then in its ionic form, it has a 2 plus charge. So 2, 2, 2. Okay, so now let's go over oxygen. So I'm just going to erase my notes here. And of course, you can always rewind the video or pause the video if you need to. So oxygen is in row 2. So it has 2 energy levels. And it's in group 6A, so it has 6 valence electrons, 2 in the first level, and then 6, it has 6 valence electrons. Ooh, I'm confusing myself. Don't worry if you're confused. I still get confused sometimes. 1, 2, 3, 4, 5, 6. Okay, so oxygen has 8 total electrons and 6 valence electrons. All right, so oxygen has 8 protons, 8 total electrons. So if oxygen wants 8 valence electrons, it's probably going to be easier for oxygen to gain 2 electrons rather than lose 6 electrons to become like helium, which only has 2. And oxygen is also a non-metal, so oxygen would prefer to gain electrons. All right, so let's see what oxygen would look like if it gained electrons. So again, we would have 2 electrons in the center, and in order to have 8 total electrons in its outer shell, oxygen has to gain 2 electrons. So now it has 8 valence electrons. Okay, so oxygen still has 8 protons because that's what defines its identity. But now it has 10 electrons. So if we kind of parse out the charges here, we have 2 negative charges left over. So 8 of the protons will cancel out 8 of the electrons, but we still have 2 left over. So oxygen is an ion here, and it has a 2- charge. Now, there isn't really a great way to remember the charge on oxygen. We'll talk about one trick later on for remembering the different charges on different ions. Okay, and then last but not least, let's go over bromine. So bromine is in row 4, and it has 7 valence electrons. So I'm going to skip drawing all of the electrons for bromine because it does have 35 electrons. So instead, I'm just going to draw the 4 energy levels for bromine, and then the 7 valence electrons in the outer energy level. So just assume that the other energy levels are already filled in with electrons. So if bromine has 7 valence electrons, it's going to be a lot easier for bromine to just gain 1 more electron rather than lose 7 electrons in order to become like a noble gas. So once it gains 1 more electron, it will now have 8 valence electrons. So now it's happy, it's stable, and if we compare protons to neutrons, bromine's atomic number is 35, so it has 35 protons, and initially it had 35 electrons. But once we add one more electron, it will have 36 electrons, and that's going to leave us with a 1 minus charge on bromine. Okay, so hopefully that helps with visualizing what's going on here. So again, let's talk about some tricks to remember the different charges on these elements or these ions. So again, we have our noble gases in this chart on the right, and these are the noble gases that the elements are trying to become similar to. So they all want the same number of electrons that these noble gases have. So helium has 2 electrons, neon has 10, argon has 18, krypton has 36, and xenon has 54. And again, I'm just looking at a periodic table and at the atomic numbers to determine how many electrons they have. So lithium has 3 electrons normally because its atomic number is 3. So it can lose 1 electron and become like helium with only 2 electrons. We saw the example of sodium and magnesium. So sodium just has to lose 1 electron to become like neon. Magnesium has to lose 2 electrons to become like neon. And then if we take it a step further, aluminum would have to lose 3 electrons to become like neon. Now, if we look at the row 2 elements, nitrogen normally has 7 electrons and 5 valence electrons. So nitrogen just has to gain 3 electrons in order to become like neon. So it would end up with a 3 minus charge. And then oxygen, we saw, just has to gain 2 electrons to become like neon. And fluorine would just have to gain 1 to become like neon. And then we can do the same thing for the other elements in the other rows. So potassium and calcium are going to lose electrons to become like argon, but then phosphorus, sulfur, and chlorine have to gain electrons to become like argon. So now, representative metals, so just the metals, will form ions having the same positive charge as the Roman numeral of the group to which they belong. So you'll notice in this group with the metals, all of the group 1A metals have a 1 plus charge, all of the group 2A metals have a 2 plus charge, and the group 3A metals have a 3 plus charge. Now, representative nonmetals, on the other hand, will form ions with a negative charge equal to 8 minus the number or the Roman numeral of the group to which they belong. So in the nonmetal group, 8 minus 5 is 3, and that is the charge or the negative charge on nitrogen and phosphorus in group 5A. 8 minus 6 is 2, and then that is the negative charge on everything in group 6A. And then 8 minus 7 is 1, and that is the negative charge on everything in group 7A. So that's one trick to remember the charges on metals versus nonmetals. All right, so there is a term for the ions and atoms that have the same number of electrons, and that term is isoelectronic. So isoelectronic literally means same electronic, and this is used to describe atoms or ions that have identical electronic configurations. So for instance, oxygen initially has the electron configuration 1s2, 2s2, 2p4. because it normally has 8 total electrons. But the oxygen ion, it has the electron configuration 1s2, 2s2, 2p6 because it gained 2 electrons. Now we can compare that to the noble gas that it's trying to become, which is neon. And that's the closest noble gas to oxygen. And neon's electron configuration is 1s2, 2s2, 2p6. So the oxygen ion and neon have the same configuration. And that's the same for fluorine, the fluorine ion, the sodium ion, the magnesium ion, and then the oxygen ion, which we just covered. They all have the same electron configuration as neon. So fluorine just had to gain 1 electron. Oxygen had to gain 2 electrons. Sodium had to lose an electron, and then magnesium had to lose 2 electrons. So everyone's just trying to become like the really cool noble gases. Okay, so next time we'll start talking more about ionic bonds. So I will see you in the next video.